Okay, so we are talking about the natural modes, or they are also called the resonant modes. I'll explain in some time today why they are called resonant modes and what the term resonance means over here. Of vibration of a stretched string.
So when frequencies of two different waves match, the resultant wave starts oscillating at a maximum amplitude. That's called resonance.
Yeah, or another way to express it is that if you have an oscillator which is of a certain frequency and you have a system like a string with a fixed length in this case, and the resonant and the frequency of the natural modes of vibration, one of the frequencies matches with the oscillator's frequency, then oscillations in the uh, oscillator can cause natural vibrations to occur in that string, and that situation of that easy transfer of vibrational energy from one oscillator to a medium, because the oscillator's frequency matches the natural modes or the resonant modes of vibration for that medium. That process is called resonance. So the first case that we saw of this was a string with both ends fixed. So when both ends are fixed, then the two ends of the string should form nodes in the standing wave pattern. So the possible standing wave patterns are ones where vibrations like this can happen. That either the two ends are consecutive nodes, or no, that is in the case of traveling wave pattern. Jagannath, that is in the case of a traveling wave that is created by a simple harmonic oscillator, which is attached to one end of the string, and the other end of the string is at infinity. But here we're talking about a slightly different situation. So I'll come to resonance, don't worry. But first, let's understand the resonant modes of frequency. So the fundamental mode here will look like this, the mode in which it can vibrate like this, where the two ends are nodes and the midpoint is an antinode. So this will be the case of the fundamental mode, where the length of the string becomes lambda by 2. So the frequency of the fundamental mode becomes 1 by 2L square root T by mu. Now similarly, the first overtone becomes the mode in which we have the next highest possible frequency. So for that, what should happen is that the string should vibrate in such a way that the two ends are nodes, but there's one more node in between. So there are 3 nodes and 2 antinodes. So distance between consecutive nodes is lambda by 2, as you've seen in standing wave pattern. So here in the first overtone mode, so that L becomes lambda. So the frequency of the first overtone becomes double of the frequency of the fundamental. And like that, the second overtone mode and the third overtone mode and so on and so forth, that series of overtones, it continues such that in the next possible overtone compared to one more half wavelength is accommodated. So in the fundamental, the whole string forms 1 half wavelength. In the first overtone, it forms 2 half wavelengths. In the second overtone, it forms 3 half wavelengths. So L is equal to 3 into lambda by 2. So like that, in the nth overtone mode, the length accommodates n plus 1 half wavelengths. So the frequency of the second overtone becomes 3 by 2l square root t by mu. So that frequency is 3 times the fundamental frequency. So like that, here the frequency of the nth overtone mode becomes n plus 1 by 2l square root t by mu. So as you can see, that becomes the n plus 1th multiple of the fundamental. So this series of frequencies is called the natural modes of vibration, or the harmonic series. So for this situation where the string is fixed at both the ends, this is the harmonic series, or the natural modes, F0, 2F0, 3F0, like this. Okay, so anyhow, this is something that we have learned about last time already. So let's look at a couple of questions based on this. Okay, so a couple of things to understand about this. The first overtone mode frequency that we're seeing here, which we denoted as F1, it was 2 times F0. So because it is 2 times F0, it is called the second harmonic of the fundamental. Okay. So whatever number we multiply the fundamental with, that is called the harmonic of it. Okay, so if F0 is, for example, 20 hertz, then 60 hertz will be called the third harmonic. Okay. 160 hertz will be called the eighth harmonic. Okay. 200 hertz will be called the 10th harmonic. So that is the name of the term harmonic in terms of resonant modes. Earlier, you have seen a different definition of the term harmonic in terms of a harmonic function in mathematics. A harmonic function is a sine function, but here it has a different meaning in terms of resonance. Okay, it is the multiple of the fundamental that is called the, okay, because here you can see that 3f0 60 hertz is this, okay, or 8f0, it is the 8th harmonic of f0, which is 20 hertz, okay, or 10f0, which is 200 hertz, that is the 10th harmonic of 20 hertz. So in this case, the first overtone mode becomes the second harmonic, okay. The second overtone mode, f2, is the third harmonic. The third overtone, f3, is the fourth harmonic, and so on and so forth. So the general formula is that the nth overtone mode frequency is equal to the n plus 1th harmonic. So harmonic is just another word for multiple. So n plus 1th harmonic of the fundamental. So this statement only we will write like in a formula by saying it is n plus 1 times f0. So that is the case when the string has a rigid boundary at both ends, or it is fixed at both ends. Yes, we will discuss other cases also, Jagannath, don't worry. So the first case over here is the case where there is rigid boundary at both ends. Okay. So this is the formula for the harmonic series. Okay, that the nth overtone mode has a frequency equal to the n plus 1th harmonic of the fundamental. Okay. Now the other point we'll discuss about is the concept of resonance, which I was telling you about. Resonance by definition over here in wave mechanics is a process by which two media or an oscillator and a medium or a system, okay, can transfer vibrational energy from one to the other naturally, okay, if their frequencies, that is natural frequencies of vibration, match. Okay. So an example of this would be that you have this kind of system where you have a string which is tied between two rigid supports. So this is a particular medium, okay, that is capable of vibrating at certain natural modal frequencies. So this is a string okay, that vibrates in modes or natural modes, which we just now saw. The fundamental is 1 by 2L square root T by mu. First overtone is 2F0, second overtone is 3F0, and so on and so forth. Fn is n plus 1 F0. Okay. Now, if we bring another oscillator like a tuning fork, like this is a tuning fork, which is of frequency F. Its own natural mode of vibration is at a frequency F. So if we give the tuning fork some energy, it will vibrate at its natural frequency F. So if this string, being a medium, okay, is next to this tuning fork, which is acting like an oscillator. Okay. So if the oscillator or source of frequency F is brought near but not in contact, just brought near. So it's not in contact, but it is brought near the medium, which in this case is the string. Okay, and made to oscillate. And the frequency of the source is equal to the frequency of some overtone. So here the oscillator's frequency matches some overtone mode of the medium. Then we will observe that the string starts vibrating with a large amplitude. Okay, even though it's not directly given any energy, okay, even though it is not brought in contact with the oscillator. Okay. So this phenomena is called resonance. So this is observed in all sorts of systems in everyday real life, not just this exact system. Another example of it could be like, you have a window pane in a wall. If a machine, like for example, a vacuum cleaner or something, okay, makes sound of a frequency equal to one of the natural modes of the glass pane, then it can start vibrating rather violently in resonance. Okay. So these kind of things can be observed very often in everyday real life, okay, where you have some kind of a source of sound or large amplitude source of vibrations, like a machine or an oscillator or a tuning fork or some musical instrument or even anything like that. which is creating sound at a specific frequency, which happens to match the frequency of some other system or some other medium in its environment. Okay. And the moment that happens, that medium or system starts vibrating with a large amplitude, even though directly we have not given it any mechanical energy or we have not attached it to the oscillator. It's not in physical contact with the oscillator. Okay. So there's an easy transfer, there's a natural easy transfer of energy from the oscillator to the source, because the oscillator's frequency is in resonance, we say, with the natural modes of vibration of that particular medium. And that resonance facilitates this easy transfer of energy, creating the high amplitude standing waves. And this phenomena itself is called resonance. So actually, resonance experiments are part of the physics lab experiments you are supposed to do at 10+2 level. Now, hopefully, in some time, you will be able to visit physics labs and start your experimental physics part of the course for these 2 years, which you have been deprived of so far because of the pandemic. So hopefully when that happens, you will get to do some fun stuff with experimental physics. Okay, so hope you have understood and written down the definition of resonance. Now let's look at an example based on this situation. So this is actually based on a type of experiment in physics called a sonometer experiment, which incidentally, as I was telling you, is one of the experiments part of your 10+2 physics lab course. Anyhow, so what we do in this is like we set up a string, let's say, of a known linear mass density, which we would have measured beforehand. And the other end of the string having gone round the pulley. So it's a comparatively light string, at least compared to the weight of the block that we are attaching over here. So this section of the string from here to here, where it's in contact with the pulley, that is of length L. And the string, this is string comparatively light string of linear mass density mu. Now a tuning fork of frequency F is brought here. Okay. Now the question says that the tuning fork of frequency equal to, let's say, 500 hertz resonates with the string in its third overtone mode. Okay, when m is equal to 50 kilograms. Okay. And so let's say just this information is given to us. M is equal to 50 kilograms. Now an additional mass m prime is added, that is, it is fixed to m. Okay. And the same tuning fork now again resonates, okay, but with its second overtone mode. So find the value of m prime in kgs. Okay. And so that's the first thing we have to do. And secondly, if the linear mass density of the string was 0.4 gram per centimeter, then find what was the length of that part. Okay, so just try out this question, people. Then we will be through with this part, which is resonant modes of a string with both ends fixed. Okay, so let's discuss these answers quickly. Okay, so in the first case, what we are getting is that, the answer of the first part is this frequency should be equal to the third overtone mode. So this frequency should be equal to fourth harmonic of the fundamental. So F should be equal to 4 times 1 by 2L square root T by mu. And in this case, the tension will be equal to mg. Okay. So this F is equal to 2 by L square root of mg by mu. That's one equation. Now with mass m prime added, okay, the new tension T prime becomes m plus m prime g. So the same frequency now becomes the second overtone. So it is the okay, but this is a different this thing, okay, because now the fundamental is this, whereas for this one the fundamental was this. Okay, with the mass added, so the same frequency F is now equal to 3 into 1 by 2L square root T prime by mu, or F is equal to 3 by 2L square root m plus m prime g by L. So this is my second equation. Okay. So basically it's like this, that when I have just mg attached here, at that point of time, this tuning fork of F was causing this to vibrate in the mode like this. Okay. And when I added mass to it, but without changing anything else, okay, this length remains the same. This tuning fork's frequency remains the same. But I just added mass. Let's say. Now the same tuning fork is causing it to vibrate in the second overtone mode. It will vibrate like this. Okay, so if you just compare the two equations, see that 2 by L square root mg by mu is equal to 3 by 2L square root m plus m prime g by L, sorry, by mu. You can just square both the sides. Okay, so 4 mg is equal to 9 by 4 times m plus m prime g. Okay. So m plus m prime is equal to
16 mg by 9.
9m. So m prime should become 16 by 9 minus 1. So that is 7 by 9.
Yes, sir.
Is that correct? Okay.
Yes, sir. Yeah.
This is the mass we have to add.
Yes, sir. Got it, sir.
Okay, good. As you can see, for this part, we didn't need even to know the frequency, the linear mass density, and all that. We just need to know this relationship. And yeah, now let's calculate the answer for the second part. So I had given this as 50 kg. So obviously m prime, you got it correct. It is 350 by 9. Very close to 39 kgs. Approximate up to first place of decimal. Up to units place. Okay. Now The second thing, let's see. So that will just come from the first formula only. F is equal to fourth harmonic. It was 500 hertz, I think. That is 2 upon L times square root of we take G as 10 divided by 0.01 when I do it in SI units. Okay. So 500 is 2 by L into 100 root 5. So L will be 2 by root 5 in meters. Or 0.4 times root 5 meters. Okay, so if you take the value of root 5, approximately 2.24, which is very close to 90 centimeters.
Sir, mu will be 0.04.
I'm sorry, it was 0.04, was it? Okay, my mistake. Yeah, 4 grams, 0.4 grams per centimeter. So 0.04, this is then, so this is so another by 2. So this is then ultimately how much? 1 by root 5
Yes.
meters. Okay. So it's close to 45. It's about 44.6 something in centimeters. Okay, so people hope all parts of this question were clear. Okay. So like these kind of things are quite simple, as you can see. Okay. Now let's see the second kind of situation where we have a string with one end as a fixed boundary and the other end has a flexible boundary. So we discussed something like this when we saw reflection of a pulse at a boundary kind of situation. So we have a fixed pole which has a smooth surface, and the string is attached to a ring which can slip freely on this. And this is a ring which can slip freely on a pole. Whereas the other end of the string is fixed to a rigid wall. So then what happens is that this end of the string, it becomes a fixed boundary. So it becomes a node in any vibrational pattern, whereas this end acts like a flexible boundary. So it acts like an anti-node. So this string will have that kind of property that anytime it is in vibration, it has to vibrate in a mode such that these two ends of the string, respectively, they are node and anti-node. So the fundamental mode will be one such that they are node and anti-node consecutively. So that means there's nothing else in between. So the fundamental mode will look like this, where this ring oscillates between these 2 points. It's an antinode and there is no other node or antinode in between. So the length of the string actually becomes equal to lambda by 4, the fundamental mode. So the fundamental frequency becomes 1 by 4L square root T by mu. So like that, now the first overtone mode, the first overtone mode will be one where this is an antinode and this is a node, but there is another pair of node and antinode, node and antinode in between. So the string, when it vibrates, in this kind of shape. So you can see that it like forms 1.5 loop. Lambda by 2 is the distance between consecutive nodes, and that's one loop. And lambda by 4 is 1/2 loop, which is the distance between consecutive node and antinode. So in the first overtone mode, the length is actually, okay, so it is 3 lambda by 2. So the frequency of the first overtone, you can see, will become 3 by 4L square root T by mu. So this has a different formula compared to what we've seen. The first overtone here is the third harmonic of the fundamental. That means the second harmonic does not exist. So in this kind of a system where one boundary is rigid and one boundary is soft or flexible, we'll see that in the resonant series or natural modal series, there are only odd harmonics that exist. The even harmonics do not exist. So this forms a different type of mathematical series for the natural modes of vibration. Okay. So just make a quick run through of this, and we'll discuss further.
Sir,
Yes, yes, beta.
so for the first one, first overtone mode, it should be 2F0, no?
Sorry, come again, beta. For the first one.
F1, sir, in first overtone mode, it should be F1 is equal to 2F0, no? Or 3F0.
No. Because see, beta, what's happening now? Any system, the lowest frequency at which it vibrates, that by definition becomes that system's fundamental.
Okay.
So this system's fundamental frequency has a different formula compared to the earlier system, which had two rigid boundaries. Okay,
Oh.
that system, because it had rigid boundaries, so its fundamental mode had the formula that it was 1 by 2L square root T by 1.
Okay.
Got the point? No? Okay.
Yes. Thank you.
Okay. Okay, now you can see here that correspondingly the second overtone, for example. So the second overtone mode has to be something where again this is an antinode and a node. Okay, but there are more number of nodes and antinodes. So the least number of nodes and antinodes after the first overtone. Okay, so in the first overtone there was one pair of node and antinode. So now there can be another pair of node and antinode. So it can be, you know, node, antinode, node, antinode, this kind of situation. Okay, so this will basically have to accommodate 2.5 loops. Let's say like this. So it's lambda by 2 plus lambda by 2 plus lambda by 4. And likewise, in the third overtone, it will have to accommodate 3.5 loops. Something like this. 3 half wavelengths and 1/4 wavelength. And so on and so forth. That's how the series goes. So in the nth overtone mode, it will accommodate n.5 loops. Here, the length you can see is lambda by 2 plus lambda by 2 plus lambda by 4. So it is 2 times lambda by 2 plus lambda by 4. So that will make it 5 lambda by 4. Here it is lambda by 2 plus lambda by 2 plus lambda by 2 plus lambda by 4. So 3 half wavelengths, which are 3 loops and a half loop or a quarter wavelength. Okay. So L
7
becomes
lambda by 4. 7 lambda by
7 lambda by 4. So here the frequencies formula will become that frequency of the second overtone is 5th harmonic of the fundamental. Similarly, the frequency of the third overtone is the 7th harmonic.
7 F naught.
So the general formula of the nth becomes that it is 2n plus 1th harmonic.
So odd k terms में it is always increasing.
Yes, it is only having the odd terms. It is not having the even terms in the harmonic series. So the nth overtone mode, the length will be such that there are n loops and then a half loop. So 2n plus 1 lambda by 4. So that will show us that the frequency of the nth overtone is 2n plus 1th harmonic of the fundamental.
So it can never have an even loop, even number.
Exactly. So this type of string can vibrate in a frequency series, which is like this: fundamental, third harmonic, fifth harmonic. Only these frequencies exist in the modal series. Okay. So this is the natural modes of vibration. Okay. So nth overtone mode frequency equals the frequency of the 2n plus 1th harmonic of the fundamental. Okay, so let's see
So
another
could
type
you
of,
scroll up for a second?
yeah.
Done, sir. Thank you.
So if f equal to 105 hertz and f equal to, let's say, 147 hertz are harmonic modes of a certain string, then find its lowest possible frequency if the string is tied at both ends. That is, it has rigid boundaries. And the string has one end rigid and one end flexible. And suppose, so the last part is find the fundamental f naught if the two frequencies given are consecutive overtones. Okay. And what type of boundaries in this case? Okay, so this is more like a maths problem actually, but in the form of a resonance based question or a modal frequency based question. Just try this out, people will discuss. So basically, I'll just give you the approach, what you can try in this question, people. So see, if, for example, if the string has fixed boundaries, then the formula is that, okay, so suppose so this is some a plus 1 into f naught. So let's say that is alpha f naught, where alpha is a plus 1, and fb is 147 hertz. So b plus 1 f naught, let's say beta f naught is equal to 105, and this is 147. So we have to find f naught such that so basically f naught is going to be, so lowest possible value means such that f naught is lowest possible. Okay, so that means it is the, oh sorry, instead of lowest possible, no, we will calculate this as the highest possible, because lowest possible can be anything, no? Because frequency can even be a fraction, no? So if it is the lowest, if it is the highest possible value, then it is the HCF, highest common factor. Okay, Jagannath, let's understand this. Okay, so 105 you can see is equal to 3 into 7, and 147 you can see is 7 into 3 into 7. Oh sorry, 5 into, that's correct. So HCF is 21, right? So if F naught is equal to 21, then FA is actually the fourth overtone, and FB is the sixth overtone for both ends fixed. And on the other hand, if one end is flexible, okay, then this should be this, and this should be this. Okay. So you can see that this would be the second overtone, and 147 would be the third overtone. So they would be consecutive overtones. Of again 21 hertz fundamental, but this series is such that and that gives you the answer for the next part also. Whereas this series would be such that both even and odd harmonics would exist. Okay, people, so hope this is clear. Let's make a note of this. So with this, people, we finished the first chapter of waves, which is waves on a string or transverse mechanical waves. Please complete problems of H.C. Verma from this chapter now. Okay. And next, we'll be moving on to the chapter of sound. Okay, only today we will end our lecture here a few minutes early because I have a meeting right now. It's unavoidable. So we'll just conclude a few minutes early.
Sound is continuation of this waves only, no? It's altogether new chapter.
No, it's a continuation of wave mechanics only. So it's the second type of waves, longitudinal waves. The first type of waves was transverse waves. So we will see that the same kind of principles like general equation of wave, then amplitude, frequency, the relationship between V and lambda and F, V is equal to F lambda. Those things will be common, but just some of the physical properties of that wave are different because we are talking about a longitudinal wave now. And then again, there will be superposition of waves. So similar principles will apply for interference, standing wave. Okay. And then additionally, there will be a few things like Doppler's effect. You might have heard about Doppler's effect in sound.
Sir, and we already have that Kunz tube experiment.
Yeah, Kunz tube will be there in sound. And Kunz tube is basically an experiment to do with standing waves in sound. Just like example we discussed today of something I told you, which is like the sonometer experiment for the resonant modes of vibrations of a string where we had that pulley kind of thing. So like that, there's an equivalent in sound where you're creating the resonant modes inside a glass tube. So that one is called the Kunz tube. Okay, but the principle is exactly the same actually. So like most of the things will be common, only in the end Doppler's effect and beats. There are two additional phenomena that we study in sound, which is not part of the transverse waves. Okay. Okay, people. So that's it for today's session. Wish you all the best. Note down this last example carefully.
Okay, sir.
Yeah. Okay, Samarth, I will try to send the recording and the notes today itself.
Thank you, sir.
Okay, Vishal, bye. Wish you all the best.
Thank you, sir.
Thank you, sir. Bye.